In the last class, we did hydrogen spectrum, and we will continue with our topic. And the topic is, we are doing atomic structure. We are doing atomic structure, periodic table, and chemical bonding. This is the name of the paper that we are doing, chemical bonding. Or chemical bonds. So last class we did this problem, give an account of hydrogen spectrum and find the value of the wave number when the electron jumps from n is equal to 5 to n is equal to 1 to n is equal to 5. So a photon will be absorbed when it jumps from n is equal to 5. So we have to find out the wave number of the photon. So this we have done. So today we are going to discuss dual nature of matter. So this is again quantum mechanics. This is part of quantum mechanics. And so as a part of that, what we are going to do today first is photoelectric effect, which exhibits the dual nature of light. So from there we will go to dual nature of light. We'll do dual nature of light, and from there we'll go to dual nature of matter. So what is photoelectric effect? So photoelectric effect, light is treated as wave in many examples. So what do we mean by that? That light is basically an electromagnetic wave. So we know that light is electromagnetic wave. This we have done at the beginning of this course. So light is electromagnetic wave. This is the classical picture. So this is the classical picture, but there are examples, or there are experiments in which the wave theory of light does not work when dealing with photoelectric effect. So this is a particular example where the wave theory of light does not work at all, and that effect is the photoelectric effect. So in this case, what we have to consider in photoelectric effect is that light is composed of quantum of energy or photon. So light may not be just looked upon as an electromagnetic wave. In this case, we have to consider light as some kind of having particle nature, and that particle is called photon. So this photon carries a quantum of energy, and that energy E, so each photon has energy E, which is given by h nu, where nu is the frequency of the light, or in terms of wavelength, in the case of electromagnetic wave, is hc by lambda, because we know that nu is equal to c by lambda. So what is photoelectric effect? Like why it tells us that light is not a wave? So in photoelectric effect, what happens is that, so this is light falling. So this is light falling on what? So light falling, this is a metal surface. So this is a metal. What we have here is a metal, and this is a metal surface. So this is a metal surface. So this is metal surface, metal surface. Metal surface. And so when light, a certain frequency falls on metal surface, what we have is emitted electrons. So there are electrons inside the metal, so some of those electrons are emitted from the surface. So since electrons have charge, what we have is called photocurrent. Okay, so I think we will call it photocurrent because this current is excited by photons. So this is photocurrent. So light is falling on the metal surface of certain frequency. Any light will not do, we'll see. And then what we have is emitted electrons. So this phenomena is called photoelectric effect, and this phenomena demonstrated that light is composed of photons or particle-like quanta, what do you call light is composed of we can say particles which are called photons, and those particles are carry a quantum of energy E is equal to h nu. So how do we know that this cannot be explained by the wave theory? So you can just come. So you can do an experiment. So this is, so we can consider two axes. Okay, so this is the axis for frequency, and this is for the axis for kinetic energy of electron. So this is the axis for the kinetic energy of electron, emitted electron. So the electrons that are being emitted, so we are considering the kinetic energy of electron along this axis, and along this axis we are considering the frequency of light that is falling on the metal surface. So when the frequency is very low, so what happens? So we are going to see the behavior of the kinetic energy of electron versus the frequency of light that is falling. So when light has very low frequency, then there is no emission of electrons. So there will be no kinetic energy of electrons. So initially it will be like this, okay, and then it will increase like this. So this behavior, so this is what is called the minimum. So this is nu min. So at least so what it is, the frequency of the light should be at least nu min in order to have photoelectric effect. If it is less than nu min, then there will be no photoelectric, there will be no electrons emerging from the metal surface, and so no photoelectric effect. But if it's greater than nu min, then what happens? Then you can see the kinetic energy of the electron starts increasing. And this is very peculiar because this cannot be explained by this graph cannot be explained by wave theory. This graph cannot be explained by wave theory. Because here you see there is no, in this part there is no, no photoelectric effect, right? In this part there is no photoelectric effect. There is no photoelectric effect. And even if you increase the, even if you increase the intensity of light, so here it has some frequency, and if you increase the intensity of light, if you increase the intensity of light, what do you mean by increasing the intensity of light? If I increase the intensity of light, that means increase the electric field, because light is electromagnetic wave, so increase, say, the electric field. Increase the electric field. So even if you increase, so in this frequency range, even if you increase the intensity of light, that is increase the electric field associated with the light, there will be no photo emission. So clearly something else is happening, and only if you cross a certain threshold, which is called nu min, then only there will be photoelectric effect, and after that, as you increase the frequency, the kinetic energy of the electrons that are emitted from this surface, they also keep increasing. So this could not be explained by wave theory. So for that, Einstein proposed this equation, for which he got the Nobel Prize. So he told that the light that is emitted, the photon that is emitted, so here I have written photons. So when a photon is emitted, so photon are particle-like structures which contain energy E is equal to h nu. So when a photon is absorbed by an electron, part of this energy goes into what is called energy goes into overcoming the barrier at the surface. So this is called the work function. This is called the work function of the metal. So part of the energy is spent in overcoming the barrier at the surface, because surface always will try to prevent the electron from escaping out. So in order to that, part of this energy will be spent to overcome this barrier. So that is called the work function, and the rest will go to increase the energy of the electron. That is, so this is the kinetic energy. So this is the maximum kinetic energy of the electron. So this is the conservation of equation which Einstein wrote. So this is the photon. Part of the energy goes into overcoming the barrier at the surface, and the rest is the kinetic energy of the electron. So that is how it is. And this is the kinetic energy of the electron that I was talking about here. Or you can say the kinetic energy is h nu minus phi. So that means if h nu is less than phi, it implies that no emission, no photoelectric effect. No photoelectric effect. No photoelectric effect. So this new mean, what I was talking about, the minimum frequency that is required to order for photoelectric effect is given by phi by h. H is we know what is h, Planck's constant. So this is the relation. So this new min that I was talking about here is this. So this depends on the work function of the metal. So now what we see is this. So energy of a photon is h nu This is the energy of a photon. So this is the energy of photon. Similarly, we know that E by C is also, it is defined as the momentum of a photon. Since a photon is particle-like, it will have a momentum. So this is called the momentum of a photon. Momentum of photon. Or we can write this as h nu by c, or this is equal to h c by lambda divided by c, which is equal to h by lambda. So what we see is this. So E photon so PHO is equal to h nu, and P is the momentum of the photon is equal to, this is the momentum of the photon, and this is equal to h by lambda. Or from here we can write lambda is equal to h by p of momentum of photon. So now what we see is, so this tells us that so from here we can go to what is called the de Broglie's hypothesis, dual nature of matter. How? So this is only for photon. So this is the relation between, so this is the relation between energy of photon. This is a relation between energy of photon. The relation between energy of photon and frequency of the wave, frequency of the electromagnetic wave. And what is this? This is the relation between So this is the relation between, this gives the relation between momentum. This gives the relation between momentum of the photon and wavelength of the wave. So the first one is the relation between energy and frequency, and the second one is the relation between momentum and wavelength. So what de Broglie said that these relations, are of general nature. So what de Broglie said was this: every particle, so it's not just about photon, every particle has a characteristic wavelength lambda that is dependent on its momentum p. You can see for photon, if the momentum of the photon is p photon, then its wavelength is lambda. Lambda is h by p photon. So this is not anything particular about photon. What de Broglie hypothesis was, every particle has a characteristic wavelength lambda, and that wavelength is dependent on its momentum p. This wavelength is called the de Broglie wavelength and is given by lambda is equal to h by p. Simple, right? So we had seen this relation in the case of photon, but this is nothing particular about photon. This is true for any particle. So particle and wave, they are strongly interconnected. So that's why it's called dual nature of particle. So a particle is actually a wave, just like a photon is a wave. Similarly, a particle is a wave. Furthermore, so this was the first one, and second one was, furthermore, the frequency nu and the energy E of the particle satisfy nu is equal to E by h. And this is again from this relation between in a photon. In a photon, energy of a photon is h nu. So this is nothing particular about photon. This is in general true. So with every particle there is a wave associated. So what is the takeaway? So with every particle, like photon, there is a wave associated with lambda is equal to h by p and nu is equal to E by h. Lambda is the wavelength, so the wavelength of the wave is determined by its momentum, okay, and the frequency of the wave is determined by its energy. This is what de Broglie's hypothesis said, and this is just an extension of what we learned about photons to particles in general. And this is a problem that you can do yourself. Calculate the de Broglie wavelength of helium atom at 27 degrees centigrade with velocity 2.4 into 10 to the power 2 meters per second. Given that the mass of helium atom is 4.64 into 10 to the power minus 24 grams and H is equal to 6.625 into 10 to the power minus 34. So this is simple. So velocity is given. So momentum is m into v. M is given and v is given. So you know the momentum, and then you have to use the relation lambda is equal to h by p, and that will give you the answer. So next we are going to do another aspect of quantum mechanics, which is called the Heisenberg's uncertainty principle. This is again quantum mechanics. So what we are doing now is quantum mechanics. We are doing quantum mechanics in bits and pieces. So this is also quantum mechanics. And this is a very important aspect of quantum mechanics. So Heisenberg's uncertainty principle. So what does it tell? It states that it is impossible to measure or calculate exactly both the position, say along x direction, so position along x direction, and the momentum that is also along x direction of a particle. Specifically, what does, so this is a quantitative principle. So it tells us that delta x into delta px is always greater than or equal to h bar by 2, where h bar is this h by 2 pi. And what is delta x? Delta x is the uncertainty in x coordinate, and delta px is the uncertainty in the x component of momentum. So let us see what it means. So what it tells us. So here what it means is that, say a particle is prepared in a definite quantum state. We know the quantum state, so we'll see later what we mean by quantum state. So a particle is prepared in a definite quantum state. Particle is prepared in a definite quantum state, and then suppose we measure x. We measure x. We measure x. X means we measure x means x coordinate. We measure x coordinate. We measure x coordinate of the particle. We measure the x coordinate of the particle, and we will repeat this experiment. So this is an experiment. We will repeat the experiment many times. We repeat the experiment many times by preparing the particle in the same quantum state, in the same quantum state. So what do you mean? So we prepare the particle in a definite quantum state and measure the x coordinate. Again, we prepare the particle in the same quantum state that we had prepared before and measure the x coordinate, and we keep doing this many times. So we will repeat the experiment many times by preparing the particle in the same quantum state. We may observe a different value of x every time. So whenever we are doing the measurement, we may not get the same value, we may get different values. We may observe a different value of x every time. Okay, so like first time we get x1, then we get x2, then we get x3, so dot 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 dot. When we do it the nth time, we get xn, and all. It may be that this x1, x2, x3 may be different or may not be different. So from here, this gives delta x. So there is a way of finding delta x, but this gives delta x. This gives delta x. Delta x is the uncertainty in x. Delta x is the uncertainty. Delta x is the uncertainty in x. Okay, this gives delta x, and delta x is uncertainty x. If, for example, if we get the same value of x, we get the same value of x every time. If we get the same value of x every time, then of course delta x is 0. Means there is no uncertainty. Every time we prepare the particle in the same constant quantum state and do the measurement, we will get the same value of x. So in that particular in this particular example, delta x is always 0. Okay, and delta x is in general, delta x is the uncertainty in x. So delta x may not be 0 in general, delta x may be some positive quantity. So if is x same value of x every time, then obviously there is no uncertainty, then delta x is equal to 0. Okay, same argument can be made for x component of momentum. That is momentum. That is we prepare the particle in the same quantum state, this quantum state, and now we are measuring the momentum. And we do the experiment many times, and from there we can get delta p. So every time the value of momentum can be different, so this gives us delta p. Okay, and delta p is 0. What do delta p is equal to 0 means? That is, we get the same value of momentum. So we prepared the particle in the quantum state and measured the momentum, and every time what is happening is that we are getting the same value of the momentum. So in that case, there is no uncertainty in the momentum, and we say delta p is equal to 0. But in general case, there will be a delta p, and this delta p may not be 0. So what this thing tells us is this delta x, this delta x into delta p will always be greater than equal to h cross or h bar by 2. And this is a very fundamental relation. So what it tells that what it tells us is, if delta x is equal to 0, that is, we prepared the particle in a quantum state such that delta x is equal to 0, that is, there is no uncertainty in its position, and delta p is equal to 0, not possible. That is, we know exactly the position of the particle and we know exactly the momentum of the particle. That is, every time we measure the coordinate, we get the same value of x, and every time we measure the momentum, we get the same value of p. So that is not possible. So that is not possible. Not possible. Sorry, not possible. That's what it is telling clearly. Okay? You can see from this relation that's not possible. So if both are 0, because it's telling this times this should be greater than equal to this. Okay? So if both delta x and delta p are 0, then this condition is not satisfied. Hence, this is not possible. So if we say delta x infinity, delta x is equal to 0, that is, position is known exactly, there is no uncertainty in the position, position is known exactly, then what happens to this? You can see this relation. If delta x is equal to 0, how to save this relation? Then it can only mean that delta px should tend to infinity. Complete uncertainty in momentum. Complete uncertainty. We have complete uncertainty in momentum. Okay. So in this case, what happens? So delta x into delta p is something finite, because this is 0, okay, and this is infinity. So 0 into infinity is something finite. You don't know what exactly this is undefined, but it is finite. But if this is not infinity, if it is in a finite quantity, delta p, then this will be always 0. So that is how this inequality is very sacred in quantum mechanics. This inequality is always satisfied. So that's what it's telling. So delta x tends to 0 means delta px tends to infinity. So if we know the position exactly, then we will not know so the uncertainty in momentum will be infinite, and vice versa. That is, we can, if we say that delta p tends to 0, that is, we know the momentum exactly of the particle, then we have to sacrifice the knowledge about its position. So delta x has to be infinite, okay, to satisfy the uncertainty principle. To satisfy the uncertainty principle. Okay, so that is, so you can see how important this Heisenberg's uncertainty principle is. So we can do a problem here. So suppose you are given a particle confined in a box of length 1 meter. Using Heisenberg's uncertainty principle, find the minimum uncertainty in its momentum. We know that, so it's very easy. Delta x into delta px is greater than equal to h bar by 2. So whatever this uncertainty in x and uncertainty in p, it has to be greater than or equal to h bar by 2, or the uncertainty in its momentum should be greater than equal to h bar by 2 into delta x. That is the minimum uncertainty. So delta p minimum, that is the minimum uncertainty that will be there. It can be more than that, but there has to be a minimum uncertainty that will be equal to h bar by 2 delta x. And what is delta x here? We will say that delta x here is 1 meter. So in this problem, the uncertainty in the position is equal to 1 meter. Okay, so this is so you can now calculate using what is the value of h bar and what is delta x. We can have an estimate of the minimum uncertainty in the momentum. So today we are going to stop here, and I'll soon come back with the next lecture. Thank you.